So this is chapter 2, and the beginning of this chapter is a lot of theories um, about the periodic table and different molecules and compounds. So let me quickly go over these. The first one is the modern atomic theory and its laws. Uh, so this is just basically to explain sort of the periodic table and its trends. There are three important theories that make up the atomic theory. And the atomic theory is matter is composed of small, indestructible particles called atoms. Okay? So all matter, that's anything that takes up space and has mass, is composed of atoms. Okay? So the law of conservation of mass, the law of definite proportions, and the law of multiple proportions basically explains how those atoms interact. Okay? So again, everything is made up of atoms, essentially. So those elements on the periodic table, those are different types of atoms we have. So everything is made up of those atoms. That is the atomic theory. Atomic meaning atom, everything is made of atoms. Okay? So our next theory, to explain how atoms actually react, is the law of conservation of mass. Okay? This one states, in a chemical reaction, matter is neither created nor destroyed. So another way of saying this is the total mass involved in a chemical reaction does not change. Okay, so let's look at this. We have, here's the reaction of water, let's say. Now if we add up all of the mass on this side, so if you see here, it says this number 2, meaning we have 2 hydrogens, and you see the subscript says 2. So we have a coefficient and a subscript. So we have 2 hydrogens of 2, so we have a total of 4. Okay, so let me show you over here to kind of see this maybe. So we have H2, okay, meaning we have 2 hydrogens, but we have a 2 in front of that, so we have 2 of those, so that would be 2 times 2, which equals 4 total hydrogen atoms, okay? You always multiply those two numbers together. So if I had like 2 O3s, we want to know how many individual oxygen atoms. Then we would say we have 2 times 3, which would be 6 oxygen atoms. Not 60, that's 6 oxygens. Or here, 4 hydrogens. Okay, so let me go back. Okay, and if we look on the periodic table, it tells us how much everything weighs. Hydrogen weighs 1, and oxygen weighs 16. So in this case, there's nothing in front of it, so that means 1. So 1 times 2 is 2. So if we look at the weight, we add. We have 4 hydrogen atoms that weigh 1. So 4 times 1 is 1. We have 2 oxygen atoms. See, it says 2 of them. And they weigh 16 each. So we add this together. 16 times 2 plus 4. We have 36. Now let's look over here. Now we have water, which is 2. We have 2 hydrogens times by 2, and oxygen, 2 times 1, 2. So if we add this together, it's 36. We haven't done so much with coefficients and everything. This gets into chapter 3 a little bit, so if you're getting a little bit lost in what I'm doing here, don't worry too much about it. The point of this is, because we'll go over how to calculate this, we won't focus so much on how to calculate this, but just know, if you did know how to do it, the mass of the reactants when I add them together is 36, and the mass of the products when I weigh them together and add them is 36. So you see 36 equals to 36. So when you weigh, if you add up how much everything weighs on this side, on the reactants, it has to weigh exactly how much the products weigh. You can't create nor destroy matter, okay? Or mass in this case. So the weight of this side will equal to the weight of that side. Now let me show you an example of a problem where this could come into play. Right here. It says hydrogen filled a balloon it was ignited, and 1.5 grams of hydrogen reacted with 12 grams of oxygen. How many grams of water were formed? So here's, the same example here. So let's see. We have our hydrogen weighed 1.5 grams, and it reacted with 12 grams of oxygen. So how much water was formed? Well, let's add up the total weight. So if 1.5 grams reacted with 12 grams, so let's do it over here. So I have 1.5 grams of hydrogen, but H reacted with 12 grams of oxygen. Okay, now let's add these together. 1.5 plus 12 is 13.5, right? So the reactants weigh 13.5. So then what does that tell me about my product? My product is water in this case. Now this is just the example reaction. We don't have to always look at water, but we are. So that means since our reactants weighed 13.5 grams, we also made 13.5 grams of water. Okay? So the weight of the reactants has to equal the weight of the products. So you could just add them and know how much product you're going to make. So that's all that says. The weight of the reactants has to equal the weight of the product. So you can't create or destroy matter, okay? It can so hydrogen and oxygen can combine to make water. It can make a different substance, but the actual weight has to remain the same. Let's look at the next law. Law of definite proportions. Now let me read this to you word for word, which is kind of confusing. It says all samples of a given compound, regardless of their source or how they're prepared, have the same proportion of their constituent elements. So I wrote an interpretation of that, which says a compound has a fixed proportions of elements by mass. Okay, so let's see what that means. Let's look at water again. So let's look at the ratio of oxygen to hydrogen, their mass ratio, okay? Oxygen weighs 16 grams from the periodic table, and hydrogen weighs 1 gram, but in water we have 2 of those, so it weighs 2 total. So 1 times 2, since we have 2 hydrogens in water. So let's look at the ratio. So the mass ratio, so if I get 16 grams of oxygen, because that's how much oxygen weighs, over 2 grams of hydrogen, because that's how much weight of hydrogen is in water, and I divide those, I get 8, or 8 to 1 if you want. So water, no matter what, will always weigh 8 grams of oxygen to 1 gram of hydrogen. That's the mass proportion. Okay, so let's look at an example of this also. It says a mass ratio of sodium to fluoride is 1.2 to 1. Okay, so let's write this down. We have 1.21 to 1, and this was of sodium to fluoride. Okay? So you can see there's more sodium to fluoride by mass. So 1.21 grams of sodium per 1 gram of fluorine. Okay, now let's see the rest of the problem. A sample of sodium fluoride produced 28.8 grams of sodium upon decomposition. How much fluorine was formed? Okay, now we know that. Let's see here. Wait, hold on. Was it 28.8? Let me look. 28.8, yeah. Now we know that 28.8 grams of sodium, okay, was prepared. So how much fluorine then was in that sample? Fluorine, question mark, we don't know. Okay, so let's look at this. Let's do it in a stoichiometry way. So we have, 28 point, nope. 8 grams of sodium. That's how much was produced. And we use this ratio Because if this is sodium fluoride, if sodium fluoride is the same as this sodium fluoride, the ratios have to be the same. So it has to be 1.2, 1 to 1. Okay, so we know if this was the same sample, it's kind of like just a conversion unit if we want. Okay, same sample, there will be 1.21 grams of sodium per 1 gram of fluorine. Why did I put the sodium down at the bottom instead of at the top? Because I need to cancel it out. I have grams of sodium here that I want to cancel out with grams of sodium here. So that's why I put it at the bottom. Okay, so I do 28.8 times 1 divided by 1.21. Okay, so this gives me, multiply, divide this out, 23.8 grams of fluorine. Okay, so when I divide these two numbers together, this one with this one here, so this number with this number, I get 23.8. Okay, so that tells me if the ratio of sodium to fluoride is 1.21 to 1, and I produce this much sodium, then I have to have 23.8 grams of fluorine. Now test this out. Let's see, what if I'm lying? Okay, so on your calculator, do 28.8 divided by 23.8. So let me write that over here. So if you divide 28.8 divided by 23.8, when you do this, you will get 1.21. Oops, I can't circle very well, which is this ratio right here, 1.21 to 1. So basically this says when I divide the amount of sodium by the amount of fluorine, I should always get 1.21. Okay? And that's what that law says. If it's the same compound, you're going to get the same ratio. So for example, water. If it is water, in fact, every time I divide the weights by each other, the oxygen, the fluorine, I will always get 8. There's always 8 times more oxygen by mass in water than there is hydrogen. So if something tells me, I have 32 grams of hydrogen, okay, so we know the ratio, oops, don't say, I know that the ratio of water is, oxygen to hydrogen, the ratio equals to 8 to 1. So let's say I have, in my sample, I think this is water. I have 32 grams of hydrogen, let's say, so I'm putting it down here. How many, oxygen grams do I have? Question mark, I don't know. So if I can cross multiply if I want. So 32 times 8 divided by 1. So let me get my calculator. So if I do 32 multiplied by 8 divided by 1, 256. So how many grams of oxygen is in there? 256 grams. Okay? So when I divide these two, to test it out, so 256 divided by 32 is 8, which is what I said here. There should be 8 times more oxygen than there are hydrogen. So that's all it says. Law of definite proportions, that whatever molecule you're looking at, the ratio of weight will always be the same. The law of definite proportions, so we could do here, so what's the ratio for nitrogen to hydrogen? Well, nitrogen weighs 14 on the periodic table, hydrogen weighs 1, but there's 3 of them, okay, so you're going to do 14 divided by 3, and let me put this in the full mode so you can see it. Oh. Okay, never mind, I don't have the answer on there. Okay, so I'll do it over here. So 14 from the periodic table, file, new, don't save. So from the periodic table, nitrogen weighs 14 grams, hydrogen weighs 1 gram, but I have 3 of them in this compound, so we're going to say 3. So the ratio, if I go 14 divided by 3, so the ratio of ammonia, NH3, 14 divided by 3 is 4.66. It's 4.66, and it will always be 4.66. So if I come here, the law of multiple proportions is basically A plus B can combine in many ways. AB1, AB2, AB3, you know. The ratio of masses of B will be a whole number. So let's look at this. Oops. CO versus CO2. So the ratio of CO is 1.33. So there's oxygen weighs 16 on the periodic table. Carbon weighs 12. You always put the one that weighs the most on the top. Okay, so oxygen is 16, carbon is 12, so 12 divided by 16 is 1.33. Now let's look at CO2. The only difference between these two is an extra oxygen. So now I'm going to have oxygen, so 16 multiplied by 2, okay, is 32, divided by 12, you get 2.67. So those are just like the law of definite proportions for each of those. Now the law of multiple proportions means now let's do the ratio of these two together. So do the highest one on top, the one that weighs the most, so 2.6 divided by 1.33. And what's the difference in oxygens here? Okay, there's 2 times more oxygens here, so when I divide those numbers I should get 2. Because there's 2 more oxygens. Now if I would have done CO and CO3, for example, now what's the difference in the oxygens? That would be 3. So if I divided their law of definite proportions by each other, I would get 3 every time. Okay? Or CO to CO4 will always be 4. Now let's look at if we were doing CO2 and CO4, the difference is 2 there, so now the ratio would be 2. Anyway, so you're doing a law of definite proportions and dividing 2 of those together. Okay, so how are they different? Because the law of definite proportions applies to samples of the same compound, comparing 2 samples using the ratio of one of the same compound. So basically, we're comparing, if we're looking at NH3, the amount of nitrogen compared to hydrogen in one compound. But the law of multiple proportions is that we're looking at the ratio of definite proportions of 2 different compounds. So we're looking at CO versus CO2. So this is what we have together. The atomic theory altogether. Each element is composed of atoms. All atoms have the same mass and other properties that distinguish them from other atoms in their elements. So all atoms, a carbon atom is going to weigh different from a nitrogen atom, which weighs different from a hydrogen atom. Atoms combine in simple whole number ratios from compounds. Okay, so you never have, like you have H2O, you never have H3 halves O2. They don't combine in fractions, they always combine in whole numbers, as you can see in the law of multiple proportions. And atoms of one element cannot change into atoms of another element. So a carbon atom can combine with oxygen atom, but if you have one carbon in your reactant, you'll always have one carbon in your product. So this is the one where the mass will always be the same. So if you have water, so if we come back over here, you notice here we have 4 hydrogen atoms, 2 oxygen atoms, and 2 times 1, 2 oxygen atoms. So you have the same amount of reactants as you do products. So basically, coming back to here, what we've learned is that all atoms are unique, they all weigh the same amount, and when atoms combine, or they all weigh a different amount, sorry. So a carbon atom weighs different than a nitrogen atom. And when you start combining carbon and nitrogen atoms, or oxygen, or whatever we're looking at, they always combine as whole numbers. And you can't create or nor destroy them. So that's the atomic theory, what they've learned from the periodic table. And in the next lecture, you're going to start going into, well, what is an atom exactly? So you can see the sort of the properties of them, but what is it? And so we're going to go into the different theories a little bit. So basically, in an atom, you'll have your protons, neutrons, and outside of it, you'll have your, electrons moving around. So good luck with that. And honestly, don't stress as much uh, with these theories, okay? I'll ask you a little bit about them, but the main thing to know is that, atoms are unique. A carbon atom is different from a nitrogen atom. They're going to weigh a different amount because they are different. And when you combine them, they're going to combine as whole numbers. That's the big thing to learn from this. I know a lot of this can be confusing and these different theories, but that's basically what these theories are saying. Of course they have to say it in the most complicated way possible, but that's all they're saying. So, think of it in simple terms. So good luck with everything.